All right, today we're going on a bit of a quest to measure something that's totally invisible. We're talking about a force that shapes everything, from how a ball flies through the air to how the moon stays in orbit. And we're going to do it with nothing more than a simple metal bar. Let's dive into the classic bar pendulum experiment.
So this is the big question, isn't it? Gravity is, well, it's everywhere, all the time. But you can't see it, you can't touch it, so how in the world do you put a number on something like that? Turns out you don't need some massive billion-dollar facility, just a bar of metal and some really clever physics.
Right, so let's set our mission. Before we start swinging stuff around, what are we actually trying to achieve here? What's the end goal of this whole experiment?
And here it is, plain and simple. Our aim is to figure out the value of g, which is what scientists call the acceleration due to gravity. You can just think of g as the number that tells us how much faster an object gets for every second that it's falling. And the tool we're using to pin it down is the bar pendulum.
Okay, but before we can get to the fun part, we've got to understand the rules of the game and the equipment we're using. So it's time to talk about the theory and the tools for the job. So, meet the star of our show, the bar pendulum. I mean, at its heart, it's really just a solid metal bar. But it's been perfectly designed to do one thing really well: swing or oscillate back and forth from a single fixed point. Its real genius is in how simple it is.
And check this out. Look at how simple the rest of the kit is. You don't need a fancy high-tech lab. You've got the bar itself, these super important knife-edge supports that give it an almost frictionless pivot point, a stopwatch, a meter stick, and a stand. That's it. That's all you need.
And this formula? This is basically our treasure map. I know it might look a little intense with all the letters and squares, but what it's saying is actually kind of beautiful. It's telling us that if we can just measure two simple things, L, which is the effective length of our pendulum, and T, the time it takes for one complete swing, we can calculate G directly. It's that powerful.
All right then, we've got our tools and we have our treasure map. It's time to, get down to business. Let's walk through exactly how this experiment is done step by step.
The whole process is super methodical. First, you set the bar on the knife edge at a distance you've already measured. Second, you give it a very small nudge to get it swinging. Third, you time how long it takes for 20 full swings. Now, why 20? Well, it helps to average out any little errors in your reaction time with a stopwatch. And finally, you do this whole thing again and again at different pivot points along the bar to get a really solid set of data.
Okay, so the physical part is done. We've collected all of our numbers. But raw data is just, well, it's just numbers on a page until we make sense of them. This is the moment where we turn simple observations into an actual discovery.
And this is where we get everything organized. For every distance L we used, we write down the total time it took for those 20 swings. And that last column, the time period T, that's our golden ticket. That's the time for just one single swing. This table is holding all the clues we need. So, how do we cook these numbers into an answer? It's really a simple two-step recipe. First, we find T by just dividing our total time by 20. That gives us a super precise time for one swing. Then, we take that T and the L that goes with it, and we plug them right back into our treasure map formula. We do that for every row in our table, and then average all the results to get the most accurate value for G we possibly can.
And after all of that careful setting up, all that timing, and all that calculation, what's the number that emerges from the data? We get about 9.8 meters per second squared. I mean, that is just incredible. That number is the known accepted value for gravity's pull here on Earth, and we found it with just a metal bar and a stopwatch. Amazing.
So, we have our result. It matches what the textbooks say, which is great. But what's the bigger picture? What does an experiment like this really truly tell us?
This, right here, is the big takeaway. This experiment isn't just some random classroom exercise, it's a powerful way to verify our physical laws. It proves that our mathematical understanding of how gravity and pendulums work is spot on. We can literally confirm a fundamental constant of the entire universe, right there on a tabletop.
Now, of course, getting a result that's so accurate takes some careful work. You can think of these as pro tips for doing good science. Keeping the swings really small is important because it makes sure our formula works correctly. You also have to avoid any little drafts of air, even from a vent, because that can throw off the timing. And most importantly, taking lots of readings is the best way to make sure your final result is reliable and accurate.
And all of this leaves you with a really fascinating thought, doesn't it?
If we can measure the gravitational pull of an entire planet with a simple swinging bar, what other huge, fundamental forces of our universe are hiding in plain sight, just waiting to be measured with clever, simple, tabletop experiments?
And that pretty much brings us to the end of this breakdown. Let's just quickly take a look at the credits.
This explainer was based on a presentation that was put together by Farzin Sheikh.
Thank you so much for joining me on this scientific adventure today. It was a lot of fun.